I'm Michele Barbato, professor of structural engineering and structural mechanics. Oops. Oh, it's coming. Perfect. At UC Davis. I sneaked myself into the other hazards by presenting a work that is on development of multi-hazard approach for performance-based engineering, but I'm still going to talk about earthquakes. So bear with me, but we are developing a performance-based multi-hazard engineering framework consistent with the existing single-hazard performance-based engineering frameworks, and in particular with the PBE. I'm going to just introduce the existing frameworks and how we arrived to the one that we are proposing, and then discuss some of the potential capabilities through an application example, and then some conclusion and the future work that is really the funding that is allowing this theoretical development for a practical application. So we are probably all familiar with the classical PBE earthquake engineering framework. It is really a divide and conquer approach where we take a complex problem that is understanding and improving the performance of a structure by breaking down the analysis into different components that are a little bit simpler to approach when taken independently. And so we are familiar with the hazard analysis, where we try to describe probabilistically an intensity measure. Then this gives us fundamentally the input for our structural analysis. We describe probabilistically the response of the structure through engineering demand parameters. And then again, probabilistically, we connect that with the damage in the structure, and finally we find a decision variable, typically dollars or time in which the structure cannot be used, in order to have, again, a probabilistic loss analysis. And again, I'm repeating probabilistic, because one of the crucial components of performance-based engineering in general, and earthquake engineering in particular, is this rigorous propagation of uncertainties from one phase of the analysis to the next. Now, let's go a little bit closer to modern days, and we started considering the performance of structures under different hazards. I'm now going to describe all of the possible frameworks. There has been a framework for fire analysis. There has been a framework for wind engineering. There is a framework for flood, except for coastal structures. So we all in the civil engineering world understood that we really care about the performance of structures, and to do that we need to have an approach that is rigorously probabilistic. And there was the development of this performance-based hurricane engineering that is making some changes to the general framework by breaking down the original hazard analysis into three different components, where the hazard analysis really focuses on the characteristic of the sites where multiple hazards are happening at the same time. In particular, for hurricane engineering, we need to consider the effect of wind, flood, windborne debris, and rain in order to really understand the overall holistic performance of the structure. And in hurricanes, all of these hazards are simultaneous and also correlated, because fundamentally the wind force or the wind speed is driving a little bit all of the other hazards, although there are additional components that are modifying hazard by hazard. Then there is this separation between structural parameters and interaction analysis, because particularly for wind, the intensity of the load depends very strongly on the characteristic of the structure. And sometimes characteristics that are not really the one that we would consider as structural engineers. Obviously, natural period and damping ratio come to mind to everybody, but a lot of the loads that are produced on the structure depend on architectural characteristics, on shape, on the properties of the surface that are also in part uncertain, and change significantly the intensity of the wind pressures that are applied on our structure. And this is true for all of the hazards that are affecting for all of the characteristics that are affecting a structure during a hurricane event. And then after we arrive to this point where fundamentally these interaction parameters are now a new measure of the intensity of the action on the structure, the rest continues fundamentally in the same way as performance-based earthquake engineering, with a nice twist of having this consideration that is part of the methodology of chain effects. Why chain effects? Again, taking the example of wind, when our structure is subjected to damage, particularly to a breach in the envelope, you have that all of the characteristics of the structure and the intensity of the loads that are applied on the structure are changing at the same time. So if you have a breach in the envelope, fundamentally what happens is that you have now internal pressures, and you see a lot of structures that acted upon by wind simply look like they exploded, because these internal pressures typically are not the one that we designed the structure for. So as the damage progresses on the envelope or on other components of the structure, also the load that is applied on the structure is changing. And so this was the first formulation that was accounting for multiple hazards and for this chain effect in an explicit manner. So we kept building on the results of performance-based hurricane engineering for a even more expanded methodology that is this one of performance-based multi-hazard engineering. So what are the major changes? A lot on this part is still the same, except that now the hazard analysis can happen not only for simultaneous correlated hazards, but also for hazards that are interacting in ways that are maybe less intuitive. For example, you can have hazards that are happening in the same place at different times, but are affecting all of the rest of the analysis. Also, you could have hazards that are happening at the same time, but that are produced by events that are uncorrelated, and so for those type of hazards, a lot of times it's just an analysis of seeing if the two things can happen at the same time, but they still need to be included in order to correctly account for the changes that are happening on the structure and thus on the performance. There are two additional elements that are accounted for in this methodology. One is climate change. For many hazards like wind, floods, snow, there is a clear dependence on the loads on the climate conditions. So the loads that we see in current climate conditions will be different than the one that may happen 30, 50, 100 years down the line. And we need to design structures that are safe, not for the last 50 years, which would be if we were considering everything stationary, but for the next 50 or 100 years. So climate change introduces this dependency on the intensity measures on climate, which introduces also a particular time scale that is the global time scale, because fundamentally climate depends or can be represented as a function of normal time in years. And then the other is structural aging. Our structures are degrading with time, naturally. Sometimes these effects can be accelerated by climate change itself. And so we need to account for that because it affects the structure both in terms of the loads that can be applied on it, and obviously this is something that we are very familiar as structural engineers in earthquake engineering, but with the structural aging also the properties in terms of damage are changing significantly, and so we need to account for that. The structural aging introduces a separate time scale, which we call the structural time scale. This one doesn't really depend on the year in which the structure is, but is more related on the life of the structure. And so it has really an origin that is the construction time of the structure, and then it depends, the effects of that depends on how many events happen after the construction of the structure. So with this methodology, we are really able now to include several different effects. I have already talked about the climate change effects, the structural aging effects. I have discussed the fact that we can now include multiple hazards that are both correlated and uncorrelated, or synchronous and or asynchronous. I have also discussed the chain effects, but there is this first element that is interesting. We don't know yet if it is important, but it is very important, for example, for wind. But we had a question, is this effect something that is important also for seismic? And this effect is the separation of intensity measure and the structural parameters, so that fundamentally we are separating structure-dependent intensity measures and structure-independent intensity measures, and seeing how the variability of the structural parameters affects not only the response of the structure, which we are very familiar with, but also the loading that is seen in the structure. And so this particular presentation is going to focus on an application example that investigates this particular contribution that, again, is very important for wind, but we simply don't know if it is important or not for seismic. So what we did was we got a collection of seismic records. All of this comes from a paper that already exists with the following structural system. So we took, again, an existing paper that has all of the characteristics of the model, not only geometry, material properties, but also the characterization of the uncertainties that are intrinsic in the modeling of this particular structure. And again, the details at this point are not that important, but we had also a direct comparison with an analysis that was done according to performance-based earthquake engineering, both considering a deterministic structure and a random structure, which was very important to understand if the additional randomness that we are introducing by separating structural parameters and intensity measure has any relevance. These are the uncertainties that were considered. So there are uncertainties in the materials. We also considered the two different versions of the model, one that has a very simplified consideration of soil structure interaction through soil springs applied at the foundation. So there are two versions, one with fixed base and one with the soil springs in the model. And then in the structural system that we considered, in the paper that we considered, a lot of the uncertainty was in the response of the injuries. So the model that we have seen before was modeled using OpenSeas with the injured beams and injured frames with a a general equation for the moment curvature or moment rotation response that is presented here, where all of these lines are described by equations that are function of the geometry of the different components, plus they are characterized by an intrinsic variability. So what are the results? Now, we didn't have all of the results that we wanted because just a few days ago we discovered the problem in our finite element model. So we had our 50 IDAs for a random structure that were all nice and ready for presentation. And then we had to redo some of those. So we have a limited number of samples that were run. So what did we do? We did an IDA for the deterministic structure. And this is the median results is given here for the structure by this black line. Then we considered the randomness in the structure, and we used a brute force Monte Carlo approach. So we simulated a certain number of samples for our random structure. For each of those, we ran again the IDA with the same earthquakes. And then we did it again with the formulation of the performance-based multi-hazard engineering approach, where we separated the intensity measure used as the spectral acceleration at the natural period of the structure, with the difference that for this approach, each new sample of the structure has a scaling that is done with the natural period that was randomly generated by generating the sample. So what did we find? It was a little bit of letdown because, as you can see here, for the fixed structure, the differences in terms of considering uncertainty in the structure or not were already very small. And then the differences between the general performance-based earthquake engineering methodology and the new framework that we are proposing were also small. But then we said, okay, for fixed end, we kind of expected because the uncertainty in the structure are small. And so the variability in the period will be also small. What happens if we do the same things, but we had additional uncertainty coming from the soil structure interaction with the soil springs? And again, we found for this particular case, the differences are fundamentally negligible. You can see, if you really squint, some differences between the two IDAs, but I wouldn't really say that that's significant, particularly considering the limited number of samples that we used. So we went a little bit more in details to understand what is happening. Indeed, we found out that the variability of the natural period is quite small, and that in reality is also true for the soil spring model. So the question still remains, but I think we can arrive to some conclusions on that. First of all, we have proposed this performance-based multi-hazard engineering methodology or framework that is consistent with performance-based earthquake engineering. If you run the same structure, fundamentally you get the same results. However, we are able with this formulation to account for multiple items that are typically not in a PBE analysis. And we have talked about it. It's climate change, structural aging, chain effects, and this separation between intensity measures and structural parameters. We investigated that particular effect, and for this example, we find out that fundamentally that component is really not affecting our results. Now we want to figure out if this is a general result, so it's always not important. It's important in wind, but it doesn't matter for earthquake engineering. Or if there are situations in which even that differentiation can be important. And I have like 20 seconds to say that this work was really done to allow the analysis for bridge structures of the interaction between scour and seismic action, and that we are now working on combining experimental results on our flume test with the results of the analysis of the combination of the risk that is coming from scour and seismic actions on bridges. And so I will conclude with some acknowledgements to Caltrans and to PEER for the funding of this research. And thank you very much for your attention. I'll be happy to respond to any question. I just finished my time, so I guess we need to keep it short, but we should have still a couple of minutes. Thank you.